Hey, everyone. Yeah, my name is Max Koretsky, but I'm also known as the Wizard. And that's probably because I really like to talk and write about some pretty complicated stuff. Topics that sometimes are seen as mysterious, and hence the name the Wizard. And I think today we will be talking about one of the topics of that kind. I'm going to talk about why Angular and React, the top web frameworks that we have today, are so fast. Basically, I will present a few JavaScript optimization techniques that these frameworks use to make JavaScript run fast. Now, I work at AGGrid. This is where we develop the best data grid in the world. So if you need a data grid, we have a free community version with a lot of features, so definitely give it a try if you need a data grid. And I'm also the founder of Angular in-depth community. So this is where we write and publish articles about pretty advanced topics of Angular. So we will be talking about three things today: monomorphism, bit fields, and Bloom filters. How many of you know about monomorphism? Watch talks, something. OK. I think I watched a talk by Benedict from the last year. He gave a talk here about monomorphism. So today I'll give you an overview of what it is and how it is used in these frameworks. We'll also talk a little bit about bit fields, and I'll show you how Angular uses data structure known as Bloom filters. OK, let's start with monomorphism. So I do a lot of reverse engineering. I sit at the computer with a debugger and go through the sources of the frameworks. And this is the comments that I found inside Angular and React sources. So these are the comments by technical leads of the frameworks. And they talk about something called hidden class and internal data structures called fiber and view nodes. And they want to ensure that these internal data structures share the same hidden class, and that is to make property access monomorphic. So a bunch of words. When I first encountered that, I didn't really know what they were talking about. So we need to clarify today what is hidden class, what is monomorphic property access, why it's important, and also what are these data structures like fiber and view nodes. Let's start with data structures. So fiber nodes and view nodes in Angular, they are used internally to represent a template, basically. So when you define a component, this is the declaration of a component in Angular. Right? We specify the elements we want to see in a template. And so Angular uses view nodes, basically data structures that it creates that represent a template. They define the metadata that is needed to render the DOM, and it also specifies which part of the DOM needs to be updated. So something called bindings. How many of you here work with Angular? Can you show your hand? OK, about 30%. Now, the same thing in React. In React, we also define components, right? We define a template. And React uses fiber nodes. This is new React 16 fiber architecture. So it uses fiber nodes to represent the DOM. And how many use React? OK, about 40%. So yeah, so fiber nodes and view nodes are used by these frameworks to represent a template. So this is something in between the declaration of a component template and the DOM. What is common between these data structures is that they are used a lot when these frameworks process changes. So imagine there's a function called update node. And it's actually an example of a function. There are a bunch of functions similar to this one in both frameworks. And this function takes in a data structure, fiber or view node, as a first parameter. And then it reads some property. So what's interesting is that these kind of functions and the property access could easily exceed 10,000 times. So a framework reads a property from this data structure more than 10,000 times, every single time changes are being processed. So it can happen a few times per second. So you can imagine how many times the framework in JavaScript needs to have access to the property. And the problem is that for virtual machines like V8, to be able to, it's a complicated process to figure out where exactly in memory the value for the property is stored. Okay, and hence the virtual machines have some optimization techniques that they use to make the process faster. But first, let me explain to you, because when I was trying to figure out all that stuff, the question I had, why is it complicated? Why is it complicated to figure out where the value is, right? And the answer is because of something called shapes or hidden classes, right? This is exactly the hidden class that Sebastian talked in his comment. So every single JavaScript object that you write in your everyday code is represented by the JavaScript object, JS object, internally inside the VM. And there's also the corresponding shape object. So shape defines or describes the layout, which properties the object has, and some metadata. For example, the offset, where to find the value in memory. Now you might think, why do we need this shape, right? Why not put all description of the properties on the object itself? And the reason is memory save. So if we have 2 objects or 1,000 objects, right, there's no need to describe the layout every single time. We can describe the layout only once, and then link this object to the shape that describes the layout, right? In this way, we only describe the layout once, even though we have, I don't know, potentially millions of objects in memory. But then, it creates a problem. What if we want to add an extra property to an object, right? So this is the setup, and now we want to extend the object A. We want to introduce the new property W. Well, we need to introduce new shape. We cannot add the W property to the original shape, right? Because it would mean that the other object, the object B that points to the same shape, has this property, which is not true. So we need to introduce the new property and then the new shape. And then we update links. The object now, the object B points to the new shape. The same thing happens if we introduce another property. We create one more shape. And so, in fact, we end up with something called transition chains. And it means that when you try to access the property, for example, X, the original property, on the A object, which now points to the shape that is at the bottom on the chain, it needs to go through every single property upwards until it finds the shape that describes the property. Okay? And you can imagine that if you add a lot of properties in different places and modify object shape, you will have a transition shape potentially with hundreds of transitions. And so every single time when you access a property, virtual machine has to go through all that process to figure out the shape that describes the layout and memory offset and retrieve that information. So inline caching is the technique that virtual machines, particularly V8, use to make this process faster. And the idea is simple. The caching is the main word here. So every single JavaScript function is represented internally by the object called closure. And this is the object where virtual machines caches some information about the function. Which objects are used to, as parameters to this function, and the other information. And feedback vector, this is the cache. This is where a virtual machine will cache some information. So let me give you an example of how it works. So suppose we are calling the function getX and passing an object with the X property. Virtual machines figure out the shape for this object, right? And then what it can do is that it can cache the shape of the object, and then the property, right? Because we are getting access to the X property. And also, it can cache the offset, right? So the next time, when we execute this function and pass in an object that has the same shape, the virtual machine can only compare the shapes. And if they match, there's no longer need to figure out the shape, right? You can just take the cached value from the offset and use it to resolve the value in memory. And what it also does, it defines the state of the function. And the state, there can be 3 types of states: monomorphic state, a monomorphic property access, polymorphic, and megamorphic. And in this case, it's monomorphic because the function has been called only with one type of shape. So it's mono. And polymorphic is when a function has seen 4 types of shapes, up to 4 types, and megamorphic is when you've been passing objects of very, very different shapes, more than 4 types of shapes. And it is important that you pass objects of one shape to a function, so the state remains monomorphic. When I was reading sources of Angular, I found the comment by Mishka that said that monomorphic property access can be up to 100 times faster than megamorphic. So now if you take into account these 10,000 times of access during each change detection cycle, that can happen several times per second. You can imagine the kind of impact monomorphic property access can have on the speed. And so frameworks use this to create, actually what they do, they want to enforce that this function that takes these nodes uses the same shape, same hidden class for fiber and view nodes. And that makes property access monomorphic. How did they do it? Well, in JavaScript templates, you can have different type of nodes, HTML elements, child components, text. And if you follow object-oriented programming principles, you would create different classes for different elements. But these frameworks actually merge everything into one data structure, one class, with all set of fields, and they use one tag field to distinguish between types of nodes. So this is the code from React framework. This is the function that is executed for every single DOM element, so potentially thousands of times during each reconciliation cycle. And you can see here that they try to distinguish by tag and then run the corresponding logic. OK, so that's monomorphism. Now let's talk about bit fields. This is the other thing that both frameworks heavily use. And a bit field is pretty low-level concept. Those who have programmed with C++, for example, know this data structure. And bit field is basically just an array of bits, zeros and ones. You can define a bit field today in JavaScript. Just type in 0b prefix in console, and you will get the binary field. Now, React uses bit fields to encode side effects. So side effects in React are basically just operations that the framework needs to do on DOM elements. Maybe place an element in the DOM, update text, remove element. And instead of having an array of strings, for example, that define operations, they just assign places and say that, OK, the third bit is the update operation. So if the bit is 1, I know that I need to update text. If the bit is 0, it means that there is nothing to do here. And I found that when I was debugging React, I'm sitting with the debugger, and I'm following the spawn element, the fiber node corresponding to spawn element. And I have just updated the text on the spawn element. So I'm trying to figure out what changes it will have. So the effect tag is this effects field. And it's a bit field. So right after the render phase, when React have process changes, the value is 4. And because it's a bit field, it's binary, so I converted it into, here it is actually the decimal, but I know it's binary. So I converted it to binary and got 100. And if you explore the effect tags field, you can see here that it's the third bit, and that's exactly what I expected. React encoded the update operation. So later, for example, here, when the function update host effects is executed, so React will check every single bit and see what kind of operations it needs to perform. For example, update will update the tags. Now, you might be looking at that and think to yourself, well, why bother, right? This is OK, this is speed, but it's still too low level. But there are a number of benefits and advantages that bit fills have over other types of data structures. For example, with bit fills, there is no need to allocate memory for JavaScript objects and shapes. So the virtual machine can save a lot of space. And because there is no shapes and JavaScript objects, there are no references, it means that the garbage collection is a lot simpler. You no longer need to figure out the dependency graph and know which objects are safe to remove. With the bit filled, it's just one instruction to processor to clear the contiguous memory, and that's it. Also with bit fills, it's a smaller and contiguous memory usage, and it also allows for fast access to check a single bit, right? It's just one bitwise operator, and that's it. So that is bit fills, heavily used by both Angular and React. And the last data structure I want to talk about it is Bloom filters. And it's a very interesting data structure. This data structure is designed to answer one simple question. Is element in a set or not? Right? Well, you can use an array, of course, and just go over each element, make a comparison, and figure out whether there's an element in a set or not. But it's quite long, right? You can imagine that if you have 1 million objects, you need to go through every single one. And it's pretty long. Well, Bloom filters allows you to do that with just one operation. So I'll show you now how to do that. But what's interesting about Bloom filters is that naturally you can get two types of answers, yes or no. And when you get the answer no, it means that the element is definitely not in the set. But when you get the answer yes, it's not actually yes, it's maybe. The probability varies. And because of that, this data structure is called probabilistic, right? There's probability here. You might be looking at that and thinking to yourself, who needs a data structure that doesn't give you correct answer, right? Well, this data structure is used most often when you expect the answer no most of the time. And this is exactly the case that I'll present to you now. But first, I'll show you how this data structure works. So each element in the set is encoded in a bit field. One bit field or a few bit fields. You will have a hashing function that will take a value and produce some number. For example, for John, if we run the function and we get the number 2, for example, if we use the first letter and the code, for the letter, we will just use a binary OR operator to set the second bit. And later, we will use the same function to get the number for John, but now we will use the bitwise OR operator to check if the John is here. And you can imagine if the bit is not set, if it's 0, it means that John is not here. Now, what the problem is, why yes is not guaranteed. The problem is collisions. So if we use the same hashing function, and we, for example, used only the first letter to figure out the number, we're passing John and Jane, they have the same first letter. Here we have a collision, right? So we may end up with the John being in the set and Jane not being in the set, but the hashing function would produce the same value, and we may get a wrong wrong result. So where does Angular use this? It uses this in a dependency injection system. So the cornerstone of a dependency injection system is an injector. It's a service, a container, where you can configure the dependencies between services, and then the injector is responsible for instantiating them. And whereas most systems have only a single injector called global injector, Angular has a hierarchical dependency injection. So for the hierarchy of components, it creates an injectors. For each component, you get an extra injector. So you end up with a hierarchy of injectors. And let's say that the widget manager service is provided in the topmost injector, but the bottommost component requires or depends on the widget. So Angular would have to go through every single injector to figure out where exactly is this service, and only when it reaches the bottommost injector, it will be able to resolve the component. And you can imagine it could take quite a while. For example, if every single injector has 10 dependencies, 10 services, it would need to go through every single one of them and do comparison, which a long time. So what Angular does, it introduces a Bloom filter for every single injector. And with Bloom filter, as I showed you, it's just one operation to know whether the service is in the set or not. And as I told you again, most of the time the answer is going to be no, right? Because we don't actually define a service in multiple injectors. So no here, no here, no here, and the topmost, the answer is maybe. And if we get the answer maybe, then we can do actual comparison and find the service if it's there. So that is Bloom filter for you. Okay, so here's a bunch of articles that, if you're interested in that kind of low-level details, I've written about reverse engineering, because I've reverse engineered all web frameworks, Webpack, Plunker, other tools. Also written about change detection in Angular and reconciliation in React. So here are the articles for you to check out. Also, if you want to learn more about this kind of topics, you can follow me on Twitter. I regularly write about some findings that I pick in these frameworks. And I've also written about my journey. The article you can also read. So I hope that the knowledge that I've told you today has awakened your curiosity to learn more about this kind of stuff. And I want you to never stop learning, and by doing so, you will be able to reach new heights every day. Because I want you all guys to be extraordinary engineers. Thank you for your attention, and good luck.